Hello, chemistry students. So we are now looking at covalent molecules. At this point in the school year, we have learned about ionic compounds. We've talked about formula units, things like that, and we will revisit some of those terms. But we are beginning covalent molecules, so we are trying to get an appreciation for some of the background and some of the theory in these covalent structures. All right, so just reviewing, this is an ionic lattice, right? It is that repeating pattern that the ionic compounds would form. The cations and the anions are electrostatically attracted to each other. All right, that's just a fancy word for the attraction. Think of like a magnet. The two opposites are attracting. Same thing's happening in an ionic compound. All right, and this is the shape it looks like at the atomic level. All right, well, an ionic compound is not a true molecule. I've come across that phrase and I always found it very interesting. Ionic compounds are not true molecules. All right. That's why we need to look at the formula unit of an ionic compound. All right. That's the simplest ratio. But a molecule has a very specific shape. All right. A molecule is its own thing, right? It is not like the ionic lattice structure, which will repeat again and again and again for just literally billions of atoms. All right. So molecules are very small in nature. We're dealing with a handful of elements. All right. And they have these very specific shapes. And if we were in school, we would build them with ball and stick models. All right. There's a couple of different models we can use to represent the molecules. But the important thing to think about is the molecules have covalent bonds, right? There is a sharing of valence electrons, whereas the ionic bonds that have those gaining and losing of electrons to make the positively charged cations and the negatively charged anions. All right, so we did see polyatomic ions. All right, these are ions on their own, but the structures they are, and if you remember, I referred to them as like the honey bunches of oats or the clusters of atoms. Well, these are actually covalent molecules that just overall have an ionic charge. All right, so again, an ionic compound, it's an individual formula unit, and it's the smallest piece of that repeating pattern, but a molecule is its own shape. All right, it's its own thing. We're not simplifying at all. It is whatever it may be. All right, so we're going to see a whole bunch of different types of molecules. And they're going to have these funky different shapes, and we could build them. All right, if you were bored at home, you could totally build some of these molecules using some toothpicks and some gumdrops. All right, and you could have some fun with that. And it's very important that we are looking in the upper right corner of the periodic table. All right, covalent compounds, covalent molecules are based on non-metals. All right, so carbon is a great example of a covalent compound structure because it forms four bonds. Carbon by itself can form all of these different structures. All right, you might be familiar with diamonds. All right, diamonds are carbons and they are carbons held together in a covalent network. It is incredibly organized, it's incredibly strong. All right, the graphite on a pencil is also carbon, but it's not as organized. There are gaps in between the layers, and so that's why the friction on the paper will break it off, and you'll actually leave a little bit of that graphite behind. All right, if you're using a mechanical pencil, that is why you have to replace it. All right, because you are literally leaving some of those carbon atoms onto the paper. All right, and there's some really fun science fiction type stuff that is real. These full arranged structures, they can make little balls out of carbon, nanotubes, and graphene. All right, the graphene is technology that's being used in different types of advanced carbon fibers. All right, graphene is certainly used in like certain golf drivers. All right, so it's super lightweight, but it's super strong. If you have anything that is carbon fiber based, I bought a carbon fiber bike. All right, and so the bike is really light. All right, but it is still very strong. All right, because it has this network of carbons and they're all covalently bonded together. Now, these are covalent network solids. These aren't what we're truly looking at, but they do show covalent bonds. We want to get to covalent molecules, so we want to think of much smaller stuff. All right, we want to think of stuff like water, H2O, and carbon dioxide, and we have a bunch of other fun examples here. Okay, so these are non-metals, multiple non-metals. We only have a small section of non-metals. All right, the metalloids, which we see in green here, they'll want to join in. So we'll see boron and silicon sometimes, but we won't see those further down ones. All right, so we're really thinking, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, and so bromine and iodine. We really won't even see much selenium. It could show up. And we will have hydrogen. All right. Now, the noble gases are not really going to make much of an appearance. All right. The noble gases think they're super cool. They have full valence shells, right? So they have those octets, but they don't like to bond. All right. So we got some pretty funny jokes about them. So we're not going to see them much in our bonds. All right. But maybe, all right, maybe the noble gases are sad about that. We always like to think of them as kind of stuck up, but maybe they're actually a little upset that they're left out of all of this bonding. And don't worry, sometimes they will bond. All right, especially the deeper elements on the column of the noble gases. So we'll see xenon form some bonds for sure. All right, and it's really going to be fluorine that's going to be the culprit of that. Okay, so. A covalent bond is going to occur between two nonmetals, and it doesn't have to be two separate nonmetals. So right off the bat, I just want to go through. There are 7 diatomic elements. These are elements that in nature, when they show up, there's 2 atoms of them. All right, oxygen, hydrogen, nitrogen, and chlorine are great examples. Ozone would be 3 of them. We can have multiples. All right, we'll see 4, we'll see 8. All right, the 7 diatomics, they are hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. And the way I was taught it and the way I remember it is a little poem, all right? And it is. The first letter of each part of the poem triggers a different element. So it is have no fear, all right? So that's hydrogen, nitrogen, oxygen, fluorine. Have no fear of iced cold bears, all right? Oxygen, iodine, chlorine, and bromine. Of oxygen, iced, iodine, cold, chlorine, bears, bromine. All right. Have no fear of iced, cold, bears. It rhymes. It's great. It's excellent. You might hear a slightly different version of that if you were to take chemistry again in college. All right. So have no fear of ice, cold bears. We'll even see things like P4, phosphorus, red phosphorus. It is 4 of the atoms together. S8, sulfur is typically 8 of them. It has yellow structure. The P4 is interesting because it is red phosphorus, and there is an excellent scene in the show Breaking Bad where Walter White is a high school chemistry teacher, but in the show, he starts cooking crystal meth, which you shouldn't do. Remember, drugs are bad. All right. But he actually sees a couple in a hardware store that are buying essentially certain items for the chemicals that are within them because they are also trying to make crystal meth, and he sees them buying matches, and matches, the head of the match, the red head is actually phosphorus P4, and that's what allows the match to ignite. And so he notices why they're buying it, and he actually at first suggests they buy a different brand because they'll get more phosphorus. And then he thinks about it and he's like, wait a minute. And that's when he goes up to him and he has an iconic line. He says, like, stay out of my territory. And they like run off, they get scared. And that's kind of as he begins to break bad. Okay, moving on. So what's going to happen? A covalent bond. Those 2 words are so important. Okay, co means we're going to be sharing. All right, and it's important we are only sharing the valence electrons. We are not sharing any of the inner electrons. We're going to look at hydrogen on this slide. Hydrogen doesn't have any inner shell electrons. It only has 1 shell. But covalent bond, those 2 electron clouds, those electron shells, whatever we want to think of them as, that space where the electron gets to exist and nothing else gets to exist there, well, it's going to overlap. All right, that is going to be the covalent bond. We could think of it as 2 people shaking hands, but the idea is each atom is going to contribute 1 unpaired electron, and those 2 electrons will come together. They will form a pair, all right, and they will exist in the same space. So obviously the atoms have to get close together, right? This doesn't happen if they're far apart. They got to get real close together, and there is a sharing of electrons, and those two electrons are essentially existing around both atoms. All right. And again, it's all the unpaired electrons. We can see we have a couple of different scenarios here where they're going to come together. All right. And there is going to be an overlap, and that is going to be good for the elements. We're going to get pairs of electrons. Again, one electron from each atom. All right. And that is going to make a covalent bond. All right. The technical definition, a type of chemical bond wherein two or more atoms share one or more electron pairs. All right. The important thing is that the electron is attracted to both nuclei. All right. They have to get that close together. Normally, two atoms actually try to push each other out of the way unless they have these unpaired electrons, and then the unpaired electrons will kind of find each other and they will overlap in space. All right, so we could think of it as these two dogs, and they are now sharing the two bones together. All right, so we have hydrogen, we have helium. So there's a couple of rules that govern these covalent bonds. Hydrogen and helium are kind of the exceptions. All right, these are two small elements, and they will follow the duet rule. All right, and we could think of some famous duets. We have Sonny and Cher. We have the couple from Greece, and of course we have Jay-Z and Beyonce. All right, but another duet, so we can think of musical duets. It's two people singing. All right, hydrogen and helium, they want two electrons in their outer shell. Helium already has it, but hydrogen only has one, so it's going to want to share with someone else. Okay, so a great duet that came to mind for me is a scene from a very short musical called 21 Chump Street, where this guy, I believe his name is Anthony Ramos, he sings a duet with her. And I have a link to the video. We're obviously not going to watch it in here, but I will include it in the description if you want to watch it on your own. And it's a very beautiful song, and it's kind of a fun show. So if you have the time, it's only 15 minutes. It is about a very interesting and incredibly true story out of Florida, and it is about high school kids and some other things going on in their lives. So you might find it entertaining at this point in your life. We will see. All right. But that is the duet rules. Only those two elements, they're the two elements that are in period 1 of the periodic table. As we look to period 2, all right, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Here we are going to follow the octet rule. All right, and I want you to think of octet as 8. These are elements that typically want 8 valence electrons. All right, now neon already has all 8. Fluorine has 7. All right, oxygen has 6, nitrogen has 5, so they want to get to that 8. We have seen these elements form ions. Now, again, in this unit, they are sharing their electrons instead. All right, so the octet rule, they want 8 electrons in their outer shell, their valence shell. Inner electrons do not matter here. All right, we have seen sodium give up its electron. All right, it becomes a +1 cation. We have seen chlorine gain that 1 electron, becoming a -1 anion. That is not going to happen here. There's going to be no charges in the covalent molecules. All right, so that's not what we're looking at, but yes, the number of valence electrons are there. All right, so instead what's going to happen is they are going to overlap. All right, so here is a great example. We have 2 fluorine atoms. They each have 7. Those unpaired electrons will overlap, right? That is our chemical bond, 1 electron from each atom. All right, now this is going to bring in an important new term. The paired electrons of each fluorine atom are going to be referred to as lone pairs, right? So if 2 electrons are paired off, they're not going to bond. Only unpaired electrons will go on and form bonds. Lone pairs do not bond. All right. All of the noble gases have 4 lone pairs, and that gets them to their 8 valence electrons. All right. But here, fluorine has 3 lone pairs, 1 unpaired. They come together, a covalent bond. All right. So an octet, we could think of that as like a men's glee club, right? Usually, there's these octets, 8 people singing. We're used to a duet, but hey, 8 people can do it too. All right. There's a couple of bands that have a lot of members. This is one of my favorite bands. They're called Streetlight Manifesto. They are from New Jersey. I have seen them perform in Sayreville, and it's a really scary experience because just about every time I have gone to see them, I have seen a former student somewhere in the crowd. So I try to like avoid that. All right. So that's why I don't go to see shows anymore. But they have 8 members in their band. Right. Usually bands are a little bit smaller. So octet 8. That's what we're thinking of. All right. And we can form multiple bonds to get to an octet, right? So here we have oxygen on display. Oxygen has 2 lone pairs, right? Since oxygen has 6 valence electrons, 2 of them are paired off, right? And again, that lone pair is not going to go on and form a bond, but it has 2 unpaired electrons. So both unpaired electrons in both oxygen atoms will each form a bond, right? And that would be considered a double bond. But what'll happen is we can count all of the electrons, including the bonds. So 1, 2, 3, 4, 5, 6, 7, 8. All right. We could even see it in nitrogen. Nitrogen with its 5 valence electrons, it has 1 lone pair. It has 3 unpaired electrons. So it'll go on and actually form 3 bonds. It'll form a triple bond. All right. But in doing so, if we were to count the electrons, it would be 2, 4, 6, 8, right? Each bond gets to count as 2 electrons, and it gets to count twice. It gets to count for each atom. All right. So you might think, well, that's bad math. They're double counting. That's what got the divers in trouble in the movie Open Water. All right. And yeah, you would be right. But this is the math we do when we're looking at the nonmetals in covalent molecules. The electrons in a bonding pair get to count towards both atoms. All right, so here we can see a situation where oxygen is a period 2 element is going to follow the octet rule, and hydrogen, that period 1 element, is going to follow the duet rule. All right, hydrogen is stoked to be sharing 1 electron with oxygen, and oxygen is stoked to have 2 hydrogens so it can share with each, and that's going to make H2O. That's going to make our water. All right. So the reason behind this, just trying to give you the background, right? Just hoping that you can appreciate it. We're not doing electron configurations, but hydrogen, helium are in the first period. They're in the first energy level. They only have the s orbital, the 1s. In the second period, we have 2s and 2p. Right? P can hold up to 6 electrons, so 2 plus 6, that's where that 8 number comes from, 8 valence electrons, S and P. From the third period on, we have SPD, we start even adding F, we have more than 8. So elements in the third period, the third horizontal row and down, can actually have more than 8 valence electrons, all right? Even though they don't normally have any 3D to them, right? They're 3s and 3p. They have access to it. It's like space that's there if needed, right? So in a sense, it's kind of like the size of the electron cloud just gets bigger from row to row. So once we reach the third row, we can actually get what we will call expanded octets. All right. If you've learned about the octet rule, if this is something that sounds familiar from middle school, you might have learned it as like, this is the octet rule and there is nothing else. You cannot have more than 8 valence electrons around an atom. But now that like we're at a different point in time, we have a better understanding. And because sulfur is in the third row, it has access to d orbitals, right, in its electron cloud. So it can have an expanded octet here. It would have 12 valence electrons around it because each bond counts as 2. All right. So because it's in the third row, it can expand. All right. And that would be a really big concert, right? There's a lot of room for them there. So that's like when like a rock group has like a whole symphony with them. All right. If we were to keep that music metaphor. So here are the Lewis dot structures. Another thing that you may have seen, I would hope you have seen, but if you have not, it is not that big a deal. We'll certainly be practicing with it. But a Lewis dot structure represents the valence electrons of an atom as dots. All right. What ends up happening is elements in the exact same group, and we have called them families. We say they had the same chemical properties. We'll look at this. They have the exact same Lewis dot structure. They have the same types of valence electrons, right? That's why they behave so similarly. So what'll happen is 1, 2, 3, and 4 will spread out, but will be unpaired. All right. So one valence electron, 2, 3, and 4 spread out unpaired. Now, carbon and silicon, these are great um, elements for covalent bonding because they have 4 unpaired electrons. They're going to want to form 4 bonds. But as we go into group 15 and beyond, as we go 5, 6, 7, 8, they're going to start doubling up. And again, we call those lone pairs. Again, when we say lone pair, we are not thinking of a sad fruit. All right. When we say lone pair, we're kind of thinking of that song, One is the Loneliest Number, but sometimes two can be as bad as one. All right. The idea is because they are paired together, they're not going to form a bond, right? They are those two friends in your friend group that start dating and now they don't want to hang out with anyone, right? And you're like, well, this is awful. So now you have to go out into the world and form covalent bonds and make new friends because your existing friends don't want to hang out with you because they are a lone pair. All right. So oxygen, for example, has 2 of those. It's only going to form 2 bonds. Fluorine has 3 of those lone pairs. Only 1 unpaired electron. It's only going to form 1 bond. And again, the noble gases have 4 lone pairs, 4 sets of paired electrons. So they typically don't form any bonds unless an incredibly electronegative atom can get them to bond. And fluorine is up for that challenge. All right. And what we're going to use these Lewis structures for, we're going to use them to represent chemical bonds. All right. So when we put the 2 dots together between 2 elements, that is going to represent a covalent bond. We're going to be able to do a lot of structures. We're going to do that in our next lesson. All right. So here I just want you to appreciate this is what we're going to be able to do after our next lesson in this unit. All right. And we're going to be able to take that information and we're going to be able, so this is what the Lewis structure would look like. We're going to be able to visualize it in ball and stick models and space filling models. All right, so we'll get these different structures. We saw this at the start of the lesson. We will be able to draw a bunch of these as Lewis structures once we learn all of those rules. And once we learn all of those rules, we'll even be able to start to see some bigger structures. All right, now this stuff can seem scary. What I really want you to remember at all times is we are learning the basics. We are learning the foundation. We are learning how molecules come together. We are more worried about water molecules and carbon dioxide molecules. This is a caffeine molecule. All right. It's cool. We can appreciate it, but you don't need to know every detail about this. All right. This would be serotonin. All right. When I see a molecule like this, my brain is releasing serotonin. I think it's cool looking. All right. It makes me happy. Now, for you guys, it might be releasing different molecules in your brain. It might be releasing some cortisone, which is something your body releases when you are nervous about something. So this might be making you kind of freaking out right now. All right, but try not to let it. We're just learning the principles behind bonding. If you wanted to learn more about this stuff, certainly you would want to take more chemistry courses down the road. All right, but we just want to be able to appreciate what's going on with the bonding, and we will get there. All right, so that's all I have for this lesson. It's just a good intro into what we are going to see. All right. And again, in our next lesson, we're really going to dive into how the Lewis structures work.